Welcome to today's explainer. The concept of REST is over 2 decades old now, yet we're still arguing about how to actually use it. Well, I am thrilled you're here because today we're laying down the absolute foundation for building production-ready REST APIs. If you're looking for a beginner-friendly guide covering core API design principles, you've hit the jackpot. We're going to look way beyond just standard requests and really explore the architecture that scales the modern web. Let's get right into it. Okay, let's dive into this, because I've got a slightly provocative question to kick us off. Are you absolutely sure the API you're building or using right now is actually RESTful? Most people just kind of assume that if they're sending JSON over HTTP, they're doing REST. But today, we're going to challenge that assumption completely and look at what this architecture actually requires. Here's our game plan for today. We'll start by demystifying true REST. Then we'll master HTTP methods, move into resource and URL design, tackle status codes and errors, scale up with state and security, and finally, look at how to evolve your API over time. Section 1. Demystifying true REST. So the truth is, REST isn't just about making your URLs look pretty. It stands for Representational State Transfer, and it was defined by Roy Fielding way back in the year 2000. And here is the absolutely crucial takeaway. REST is not a protocol. It's an architectural style. Think of the client-server relationship kind of like a restaurant menu and a kitchen. The client, the person ordering, just reads the menu. They don't need to know how the kitchen stores its ingredients or cooks the food, right? The UI and the data storage are entirely separated. Now, what's really interesting about this is that to be truly RESTful, your API literally must satisfy all of these constraints. It has to be stateless, meaning the server stores zero session state between requests. It's got to be cacheable. It can operate in a layered system where the client has no idea if it's hitting a load balancer or the actual end server. But the absolute cornerstone of the whole thing, the uniform interface. All interactions must follow a standard interface, no exceptions. And honestly, that brings us to a huge key insight. Most APIs that people call REST are actually just RPC over HTTP. They use HTTP methods and JSON, sure, but they totally miss that strict uniform interface constraint we just talked about. Now, let me reassure you right now, building an RPC-style API isn't inherently a bad thing. A lot of massive companies do it every single day. But as a developer, understanding the theoretical difference is an incredibly important insight. Moving on to Section 2, Mastering HTTP Methods. This is a really massive focus for us today. I want to thoroughly explain the proper usage of HTTP methods like get, post, and put, because they act as the primary actions for our resources. Let's start with get. A get request is just used to read a resource. It's what we call safe and independent. All that really means is it has zero side effects. You should absolutely under no circumstances ever use a get request to mutate or change data in your database. Next step, we have head. This does the exact same thing as get, but it only returns the headers, not the body, which is super perfect for just quickly checking if a resource exists. So the crucial point here is understanding the critical difference between post and put. Post is used to create a completely new resource, and it is not idempotent. If you call a post request twice, you're probably going to end up creating two identical records in your database. Put, on the other hand, replaces a resource entirely. It is idempotent. If you send the exact same put request 10 times in a row, the end state of that resource remains exactly the same as if you just sent it once. Just to round out our mental model here, we also have patch, which is used when you only want to update specific fields rather than replacing the whole entire resource. Then there's delete, which removes a resource and is also impotent, meaning deleting something that's already gone should just quietly return a 404 or 204. It definitely shouldn't crash your server. And finally, options. This one returns the supported HTTP methods for a URL, and you'll mostly see it used behind the scenes in Core's pre-flight checks. Let's jump up into Section 3, Resource and URL Design. Okay, so now that we have our verbs down, let's look at the nouns. This is the public contract of your API. The absolute golden rule here is nouns, not verbs. The HTTP method we literally just learned is your verb, so your URL doesn't need one. Notice how this action-oriented RPC style uses URLs like getUser or createOrder? Yeah, don't do that. In a proper REST API, you use plural nouns. To get a user, you send a get request to /user/42. To create an order, you post to /orders. It's just clean, it's intuitive, and it's highly predictable. So how exactly do we pass specific details? Well, you use a path parameter like that 42 in /users/42 strictly for identifying a specific resource. For absolutely everything else, like filtering, sorting, paginating, searching, you use query parameters. Notice how appending $status equals pending neatly filters the orders collection without breaking the main hierarchy. It's super elegant. Transitioning into Section 4, Status Codes and Errors. This is basically how the wiring of your API communicates outcomes back to the client. The 200 range, that means success. 200 OK is your standard, everyday success. 201 created is specifically for when a post successfully makes a brand new resource. And 204 no content means it was successful, but there's no body to return. Now, a massive mistake developers make is returning a 200 OK status code, but secretly stuffing an error message inside the response body. Please, whatever you do, don't do that. It completely breaks monitoring tools and confuses the heck out of clients. Now, when things actually go wrong, we use the 400 and 500 ranges. The 400 level codes are client errors. You messed up. 400 is a bad request. 401 is unauthorized, meaning you lack authentication entirely. 403 is forbidden, which means we know exactly who you are, but you still don't have permission to do this. And of course, the classic 404 not found. The 500 level range, however, is strictly reserved for unexpected server-side failures. That basically means we messed up. And look, when you do return an error, it actually needs to be helpful. Following the RFC 7807 problem details standard, a perfect error response includes a specific machine-readable code, a highly actionable human-readable message, a unique request ID for your logs, and a direct link to your documentation. But what should you absolutely never include? Internal stack traces or raw database errors. Exposing those to the public is a massive security risk. Just don't do it. Let's keep the pace up. Section 5, State, Scale, and Security. All right, let's look at the advanced operational concepts that take your API from a weekend side project to being fully production ready. If you're returning thousands of records, you absolutely must paginate. Offset and limit is great for admin panels where you just need to jump to page 10, but honestly, it gets incredibly slow on massive data sets. That's exactly why huge platforms like Twitter and Slack use cursor-based pagination. It returns an opaque token marking your exact position in the feed, ensuring that as new data comes in real time, your pagination doesn't drift at all. And this brilliantly illustrates one of the most critical concepts in API design: idempotency keys. Imagine a client sends a post request to process a payment. The server charges the card, but boom, the network drops before the response even arrives. If the client retries blindly, the poor customer gets charged twice. But if the client sends a unique UID in an idempotency key header, the server caches that first response. When the client retries with the exact same key, the server just goes, "Oh, I've seen this," and returns the cached response. No duplicate charge. It's a lifesaver. Protecting that API requires solid authentication and limits. You might use API keys for simple server-to-server trust or JWTs for stateless, signed tokens. You can kind of think of those like secure digital ID cards. For user-facing delegation, OAuth 2.0 is the complete industry standard right now. And to prevent abuse, you simply must implement rate limiting, using algorithms like the token bucket, and you have to communicate those limits back to the client using standardized headers so they know exactly when they need to back off. Finally, Section 6, Evolving your API. Because let's face it, once your API is live, it will change, and you need to handle that gracefully. One really amazing way to evolve efficiently is through caching to save bandwidth. Here is a super elegant flow using e-tags. The server returns a resource along with an e-tag, which is really just a unique hash of the content. Later, the client requests the resource again, but sends that e-tag back saying, hey, if the content still matches this hash, don't even bother sending it. The server checks, sees nothing changed, and simply returns a 304 not modified with basically no body. It is just incredibly efficient. To wrap up, I want to leave you with a bit of a provocative thought. Roy Fielding, the actual creator of REST, famously said that an API without HADOS, which is when the API response includes hypermedia links telling the client what actions it can take next, isn't actually REST at all. But let's be real, almost nobody in the industry implements it, opting instead for static documentation like OpenAPI. So, are we all just building RPC over HTTP? And more importantly, if it's reliable, if it's predictable, and if it scales, does it actually really matter? Keep building, keep learning, and I'll catch you in the next explainer.